I'm going to be telling you about some of the work, as Kirsten said, to develop maybe a new type of particle detection technology that really, instead of sensing the energy deposited in some very sensitive detector, we're trying to see really mechanical forces acting on macroscopic sensors. The type of mechanical sensor I'm going to focus on, and you can see an example of here, that's actually a 100 nanometer glass sphere, little tiny piece of dust that's floating in a laser. There's an invisible laser coming from the side here that you can't really see. It's focused there, and that little tiny particle is held at the focus by the light forces. If we put this in ultra high vacuum, as I'll say, we can make very sensitive sensors and then maybe even apply them to fundamental physics questions. So before I get to that, let me just show you this beautiful picture of our neighboring galaxy, Andromeda. This is really, it's amazing to see all this structure and really beautiful things that exist out there in the universe. But maybe as a fundamental physicist, a particle and nuclear physicist, what excites me most about this picture is that we know most of the stuff in this picture we just can't see. So the vast majority of the matter in this galaxy is dark matter. It just means it doesn't interact with light. That's why we don't see it. Even among the other matter particles we know are there, the most numerous matter particle for sure that's there here is neutrinos. And again, we don't see those. So some of these, very weakly interacting particles, in fact, because they don't interact with light, because they don't emit these kinds of things, also means their interactions in the lab are incredibly weak, and we might need new types of very sensitive detectors to maybe tease these out. So I'll start with dark matter. There's really compelling evidence from all the scales we look at in the universe now that dark matter exists. For the younger folks, this is going to be a whirlwind one-slide introduction to dark matter. But we've basically, we got the first hints from this maybe in the 1930s, but then in the 1980s, Vera Rubin and collaborators started to measure how these kinds of spiral galaxies were rotating. And really, maybe the exciting thing is to actually look out past the stars and see the neutral hydrogen, which also isn't emitting light, but is normal matter. If you measure the velocity of rotation of this galaxy way out past its center, the famous thing that we see is that the velocity continues to maybe be flat or grow a little bit. Whereas if you just add up all the mass we know is there in the center of the galaxy from the stuff we can see, you'd expect it to be falling off. So there's a pretty compelling story here that there's something dark that we're not seeing, and it can't even be like normal hydrogen that's just dark. We really think it has to be something new. But maybe the most solid case that there really has to be some dark component of the galaxy, the universe that makes up most of the matter in the universe comes on the biggest scales we look. And we have really beautiful measurements of a number of things at the absolute biggest scales we can see, from the cosmic microwave background to the expansion of the universe. We measure from supernovae to baryon acoustic oscillations, which is kind of the leftover ripples from the cosmic microwave background, that seeded structure that we see at much later times in the universe. And with just a few parameters, it's really amazing that we now live in this era of precision cosmology where you can fit all of these really very rich data sets together, which many people actually at Yale are working on improving the measurements of those. But if on this plot is showing the dark energy density, the fraction of the mass energy in dark energy versus the matter density, which is almost fully dark matter. And this little gray ellipse here is the combined fit to all these data sets, which really requires there be something like 5 times as much matter that's dark and really different from all the particles we've ever studied in particle accelerators here on Earth. So there's, from all length scales, from the smallest to the biggest in the galaxy, we seem to see dark matter. Now, if you've heard a talk about dark matter in the past decades, you've probably mostly heard about 2 candidates. Weakly interacting massive particles, or WIMPs, and axions. There's really exciting work actually happening outside our group on both of these kinds of dark matter candidates. And these are really important searches. These are great ideas for what dark matter could be. But we haven't in all the searches to date seen these yet. And in fact, if you look at what we know astrophysically about dark matter, basically the minimal things we know is that it has to fit in the smallest galaxies we can see. So that actually sets a limit on how light it could be here at the Zepto EV scale. I'll come back to SI units later in the talk. There's a 10 to the minus 21 EV mass. So it has to fit in our smallest galaxies on the light side. And on the high side, we can look for heavy, massive things like black holes passing in front of stars and look for gravitational lensing, which is also a purely gravitational signal. And we can mostly rule out that there's very heavy things out there. And that's kind of an agnostic view based on astrophysical evidence for what the kind of particle nature of dark matter could be. And there's a lot of parameter space here, 30 orders of magnitude, which maybe our traditional candidates don't fully cover all these possibilities. That said, as we've done more and more precise searches for these, there's still lots of places to look for these favored candidates, but the community has also stepped back and maybe looked at what we really know in light of these astrophysical constraints. And in fact, it's quite easy to write down many extremely plausible models for dark matter that satisfy all the astrophysical things we know about it, but range over this full 30 orders of magnitude in mass. And in fact, maybe all kinds of different couplings, even different phenomenologies for how they interact in our detectors. So if you're an experimental particle physicist or nuclear physicist like myself, this might be a pretty daunting picture. When I was in grad school, it was easy. We were just looking in little tiny areas. Now we have to look in all kinds of areas. So maybe it's worth stepping back and ask yourself, could you do a model independent search for dark matter in the lab? Just as a thought experiment, maybe, what would that look like? And if you want to really dream, you could imagine kind of the following. This is actually a proposal from Dan Carney and collaborators, where maybe you imagine you have a little mass sitting in your lab. The only thing we know from astrophysics for sure is that dark matter interacts gravitationally. So if it flies by this mass, it should give it a little tug. Dark matter is also massive, it's matter. So you should maybe see a little kick. And maybe if you're a theorist, you draw a little array of pendula, and you have this dark matter particle flying through and giving all these little pendula a little kick. So could you even do this in principle? Well, the first thing to think about is how still are these pendula? Are they sitting there jiggling around? If they're too hot, you're not going to see these kinds of really tiny, because gravity, as I'll say, is really, really weak compared to the other forces. So any kind of thermal noise is going to sink you. But if you plug in relatively heavy dark matter masses, this is again in SI units, but up around the Planck mass, maybe a scale of new physics where we might expect there to be heavy dark matter candidates, and you put in maybe milligram mass sensors similar to that dark matter mass, you space them by a millimeter. You can actually get, in the presence of the kind of thermal jiggle of these sensors, the ability to see, so the signal to noise squared here, so a factor of 100 signal to noise for these kinds of kicks going by. So at least if you like levitate these in an ultra high vacuum chamber where there's no jiggles from the background gas, you could maybe get the noise level you need. So I'll come back to that in a second, but what really matters is that there's no gas collisions transferring more thermal energy to it. Probably you will also cool them to extremely cold temperatures, but it's not strictly required for technical reasons. The other thing to ask is if I'm putting in a heavy dark matter, or Dan's putting in a heavy dark matter mass here because it makes it easier to see gravity. But do you get enough of these particles here on Earth? And we know basically the mass density here at Earth by looking at stars around us and how fast they're moving. We can tell in some cubic kiloparsec around us what the average mass density of dark matter is. So then if we plug in this Planck mass sort of dark matter, we might get 1 per year per square meter of these massive particles coming through our detector. And that's a little bit worrying, because if I told you I want to space these by maybe 1 millimeter, I want a meter, maybe a meter cubed of these things, it's 1 billion such sensors. So, that's going to be a daunting thing. But maybe not, like there's no laws of physics being violated here. But maybe the most interesting thing is if you can imagine doing this, if I want to see all these pendula got a little kick, I have to look at them, right? And Heisenberg says that if I'm going to look at something, my measurement itself is going to affect it. And in fact, if I'm going to shine photons or something at those photons have shot noise. And if I turn up my laser too high, they're going to push on the pendulum itself. Turns out the act of measuring these pendula is the hardest part of doing this experiment, even in theory. So maybe you can handle the noise and the rate. But if you wanted to see that these pendula were moving, maybe with a laser, then these kinds of measurement limits that come from quantum mechanics are really key. So if you're ever going to do this, Heisenberg just said you can't measure the position and momentum of these pendula simultaneously. But if you can do a smart, deeply quantum measurement that learns about the momentum, these little momentum kicks, while not learning anything about the position of the pendula, and maybe do that for the experts 30 dB or a factor of 1,000 in variance beyond the so-called standard quantum limit, or measuring at that kind of Heisenberg bound for simultaneous measurements, you could maybe imagine this. That said, this is mostly a thought experiment, and just to get you thinking for this talk, we're very far, of course, from doing that kind of thing. So, if that's possible, I think it's super exciting that the community is now talking about, these kinds of blue sky kind of thought experiment ideas. But every search we've ever done for dark matter assumes there's some interaction stronger than gravity. And in fact, when you think about it, the standard model, 20% of the matter we think is in the universe is very complicated. We have 3 generations of fermions, 4 fundamental gauge interactions. And then we have this picture where there's maybe 1 new dark matter particle. In a minimal sense, maybe it's only interacting via gravity. And it doesn't have to be there that way. Of course, that's, that would be hard to do the sorts of things I just described. But if there's stronger forces, maybe still very weak forces, but much stronger than gravity, mixing between us and the dark matter, we can already do exactly the same sorts of things I was talking about, but not have to see these tiny impulses that would come from gravity. And in fact, there's been a huge amount of technology developed for making extremely sensitive force sensors that we can control and read out using light, so-called optomechanical systems. This is work that's really pioneered here at Yale, among other places, but Jack Harris was many years ago actually already starting to study these little membranes. building on work originally in the gravitational wave community before this was maybe even called optomechanics. And now there's a huge effort. This is a nice plot from Marcus Espelmeyer's review article showing all the way from single atoms and ions over many orders of magnitude and mass up to the gram scale and then kilogram scale things in the gravitational wave detectors that we can really control a huge range of systems and measure them, in many cases approaching these kind of quantum measurement limits where the measurement itself is the dominant noise source. So this is a nice toolbox to play with if you're a experimental physicist to try to look for things that mostly give you forces and push on quantities of mass in the lab. And I'll come back to what types of dark matter models do that. Obviously, I can't talk about this whole chart today. In fact, I'm only going to focus on a very specific set of objects, ones that I can levitate. Those are the ones that maybe are most obviously I can get rid of the thermal noise and make sure that my measurement is really the dominant noise source. And those maybe live here mostly in the femtogram to microgram range for the ones I'll talk about. That said, though, there's a huge, rich number of applications in searching for dark matter, and there's a community white paper that a few of us organized a workshop a few years ago that came out of that describing many things beyond what I'll talk about here. So before I tell you about the actual experiments, let me show the people really doing the work. So in order to take us seriously as a dark matter experiment, we do have an acronym, but this is really a handful of folks working at Wright Lab. I thought this was a nice picture. This is just over a year ago at Wright Lab. You can see our group. The group's changed. We have new folks we're welcoming, but you can really see Wright Lab has even changed a bit more. And then I might not have much time to talk about it, but we also have some collaborations starting. I'll say a little more about QUIPS, searching for heavy neutrinos, and then new experiments we're spinning up to try to see if we can someday, this is also very far in the future, but entangle two of these micron-sized spheres through their gravitational interactions. So let me tell you about the actual systems we're using. Generally, these go by the name of levitated optomechanics, which just means we're using light to hold and control these particles. We're levitating things, so we're holding them up with no support in vacuum. And it's kind of amazing to me that you can levitate things over a huge mass range from maybe 100 nanometers in diameter or smaller, all the way up to tens of microns. This is more than 6 orders of magnitude in mass, from femtogram, again, SI units, femtogram, 10 to the minus 15 grams, up to nanogram masses, tens of nanogram masses, just by taking a laser and focusing it. So for technical reasons, for our smaller particles, we use a high numerical aperture, a tightly focusing objective that traps one of these particles up to about a micron at the focus of the laser. For larger particles, in order that they don't heat up too much and actually melt, we use these levitation traps, which hold them up against gravity with the scattering of photons from their radiation pressure. And these are basically, a technique that's been long around in biophysics and biology, where if you go to many labs on campus, you'll find these optical tweezers that grab little particles with a focused laser. And they've really revolutionized how we measure the piconewton scale forces, 10 to the minus 12 Newton forces that we see in those biological systems. But those are always living in some thermal bath. They're sitting in some fluid because that's where biological systems live. And if you get rid of that thermal noise, then you isolate these things extremely well from that thermal noise just by pumping the air out of the chamber, not cooling the walls of the chamber, but getting rid of the gas. And as I'll say, we also isolate them electrically so we can control their electric charge state extremely well. And we can get to these force sensitivities because of the thermal isolation really far beyond, as I'll say on the next slide, maybe what you're already used to in extremely sensitive optical tweezers. So this is showing that one of our choices about whether to use small or large particles depends on what we're trying to do. For many things like dark matter, which couple to mass, you might care about the force per mass sensitivity, the acceleration sensitivity. That usually improves as we go to heavier masses, so we might want to use these heavier levitation traps. But at the end of the talk, I'll talk about some things where we're just seeing a force hit these particles independent of its mass, and there maybe we want to go to these smaller sensors, kind of nanoscale sensors, to get the best force sensitivity. Okay. And I should just say that the same sort of levitation trap is actually the original sort of thing that Arthur Ashkin demonstrated in the 70s and got a third of the Nobel Prize a few years ago for. And we're now building kind of modern implementations of those in our lab. So I said I'm using lots of SI units. So for the non-SI aficionados, let me just maybe orient you a little bit. So this is kind of a fun chart adapted from Wikipedia showing forces over another like 30 order of magnitude span here. From the order of tens of meganewtons here for the Starship taking off at liftoff here, down to maybe, millinewtons, the weight of a feather. Here, again, at piconewton scale are these optical tweezers in fluid. And they've done really beautiful things like understand all these like nanobots walking around in biological systems. It's a kinesin motor protein, an artist's conception of a kinesin motor protein walking along a microtubule. And you can see these like micromotors kind of walking or nanomotors walking around in biology. But the sorts of things I'm talking about here, down here in vacuum, when you get rid of the thermal noise you have in those kinds of fluid-based tweezers, are really another maybe 10 orders of magnitude lower in force sensitivity. So the type of forces we're talking about here, maybe the weight of a single virus, the gravitational force between two micron scale objects, that's something like the relative force scale between these biological tweezers and the vacuum tweezers as maybe the starship at liftoff to the weight of a single feather. So these are really tiny forces that we're talking about. But of course, we need that if we're going to talk about forces imparted by single fundamental or subatomic particles. So this is what the experiment, one of the experiments in our lab looks like. These are in Wright Lab. I encourage you to stop by and take a look. We're happy to show you around if you want to see them in person. We have a couple optical traps, as I said now, levitating their nano or microscale particles. With just a little bit of laser power, again, focus in this vacuum chamber, we can trap these particles. For the AMO folks in the lab, maybe there's very few optics on this table. This is a relatively simple setup, at least in my mind. But we have a vacuum chamber here in the center. It's a vertically oriented laser for our large particles, and the particle is trapped there in the center of that gold-coated cube. And these traps are very deep, so once we get a particle trapped, it'll stay there. You know, we've had them for months, long time, until someone drops a wrench on the table or the power goes out or something. So they don't fall out on their own. Let me show you a little bit the kind of techniques we've developed to be able to manipulate these, because, you know, even though Arthur Ashkin had done this kind of stuff in the 70s, because everyone got so excited about using these in biology, we really hadn't come back to using these in vacuum for a very long time. So maybe over the past 10 years, there's been a real renaissance in the levitated optomechanics and vacuum field. I'll tell you about some of the techniques we use for the larger spheres, maybe the micron-sized objects. The first thing you have to do is get them in the trap. So in biology, they'll float by in the fluid and you just grab them with the laser. Here, of course, they'll fall in air and vacuum. So at some modest vacuum pressure, our favorite thing to do is maybe move the sphere over top the laser. And then it really wants to stick to the surface it's on by van der Waals forces or kind of surface adhesion. So we have to shake that at like 10 to the 6 Gs or something like that to pop it off. We do that with a piezo. In fact, the little video you see when this dark particle is in focus, it's sitting down there on the cover slip. We shake it, it pops up into the laser just above the focus. And in this case, we can actually pick up and set down the same particle over and over again. We've trapped the same particle in this system like 100 times or something. So now you get the particle popped up into the trap. We do this at relatively modest vacuum pressures so that the traps are still stable. There's enough dissipation that the sphere doesn't immediately heat up and leave. But then, of course, as I told you, we want to go to ultra high vacuum or high vacuum so that we can minimize the thermal noise acting on this particle. So we pump down to maybe 10 to the minus 7, 10 to the minus 8 millibar in the current systems. When we pull these glass particles off glass, just triboelectric charging, like rabbit fur on glass sort of charging, you get a lot of net charge, always extra electrons in these systems on the spheres. And so in this case, we had about 10,000 extra electrons. We apply an oscillating electric field and then just monitor the motion. We're always measuring the motion of these particles just from the laser light that's holding it up, scattering from this little glass particle, which is acting like a lens, scattering as it moves. And so if we, just like the milk and oil drop experiment, we can apply an oscillating electric field, see how much it's moving. And then as we shine UV light on it, here we see that motion decreasing, it's shaking less and less. In fact, here we go across 0. Which means we've knocked too many electrons off in this case. Now we have more protons than electrons. So we start knocking electrons back from the gold surface onto the sphere. And here, if you zoom in at the very end, you see us knocking 1 electron at a time onto the sphere until when we're at 0 here, we have exactly the same number of electrons and protons on this object that might have 10 to the 14 of each. So this object has a perfectly neutral electric monopole charge and perfectly neutral net charge. The next thing we do then is we spin these particles. It turns out that if we don't spin them, their angular degrees of freedom are flopping all over the place. So we use a little bit of circularly polarized light, which, because they either have trace absorption or some birefringence, they can absorb some of the angular momentum of that trapping laser. And actually over day-long time periods, they can just spin faster and faster up to their terminal velocity, which is something like 5 megahertz. So these things spin 5 million times a second. In fact, we can't go any faster because they explode from centrifugal stress. So these things are spinning as physically fast as possible for a normal material object of this size. And here you just see one of these particles rotating faster and faster. The damping times are so low at 10 to the minus 7 millibar here, it just spins up over days to 5 megahertz or something here. So now we have a perfectly neutral object spinning at 5 megahertz. And that means we've averaged away, if there's any higher order multipole moments in the electric charge distribution, they've averaged away except in the direction of the spin axis. And so there is a permanent dipole, electric dipole moment of this object, which is maybe the bane of our existence, but we've now gyroscopically stabilized it in the vertical direction. And as I'll say, we can maybe even do trickier things in a second. So we have a perfectly neutral object spinning at 5 million times a second in the center of our vacuum chamber. Now, if we want to, we can cool its center of mass motion, its translational degrees of freedom, with active feedback cooling. So we just watch the particle, and if it moves a little bit to the right, we push a little bit back to the left to slow it down. This is a damping, but without adding noise, so we call it cold damping in the community. This is a plot of the power spectral density in meters per root hertz versus frequency of one of these large particles here in meters per root hertz. So this is a nanometer in the center of the chart. This is just a damped harmonic oscillator. So you see a relatively high quality factor oscillator peak here at the resonant frequency of the sphere in the center of the plot when we're applying the minimal amount of feedback we apply. And then as we increase the gain, the amount of this feedback we're applying, and this is maybe to Meg's question, we slow its motion more and more, cool it down. And in fact, when we hit the displacement sensitivity of our system, the center of mass of this object is as still as though it were in thermal equilibrium with a 50 microkelvin gas. So the walls are at room temperature, and this thing is as still as though it were at 50 microkelvin. So this is an incredibly still, spinning, stable object with exactly the same number of electrons and protons. If we want to, at this point, we've shown that we can try to get rid of this dipole moment further by actually doing like the classical analog of a pi pulse in NMR, apply a torque with an electric field, push this thing over, it's acting like a little gyroscope, and in fact, we can further cancel out any effects coupling to the asymmetries in the charge distribution. So again, you'll see these are all kind of recent technical developments, but they're the kind of prerequisites to trying to do very sensitive force measurements with these systems. And I should just also say, this is really nice work from our senior graduate student, Ben Siegel. Once you have one, you want a lot of these things. So Ben's done nice work to show we can make arrays of these particles just by splitting a single high power laser into lots of traps. And of course, when you have such an array, you have to make the university logo of your school. So here's the Yale Y that Ben has made. And in fact, those are all individually controllable traps. So that's exciting. So let me just say, this is maybe the last on SI units, and then I'm going to flip to particle physics units. If you were really paying attention, you might know 2 years ago, the new official SI prefixes were added in the first time in about 3 decades. In fact, this was because people have really big data sets now, and they were calling things like hecabytes and other things. The metrologists really don't like that kind of stuff, so they convened a committee, had a really careful thought about what letters are still left and what vaguely kind of Greek-sounding words they could call these. But you read this article, it says, we added these things for the big data sets. We also added terms for the small end of the scale. We're not really sure that we're measuring anything on the scale, but it's better to have the scale balanced. And in fact, when we get our spheres perfectly neutral, we've seen as few as 1 electron maybe per week come on and off these spheres. So in some funny way of thinking, that's an average current during that week of 1 electron charge per week. So we have a unit for that that's about 100 Ronto amps. Okay. So what do we want to do with these things? In our group, we're really interested in applying them to fundamental physics. Actually, what got us, so I'm not going to talk about all this, but just to give you a flavor, what got us into this game was trying to test fundamental force laws, test Newton's law down to micron distances, shorter distances than people have been able to verify that Newtonian gravity works just like it does among planets. We've done things like float a sphere off the surface of a microfluidic capillary that has different density fluids flowing behind a gold-coated surface and try to see gravitational interactions between the sphere and these different density masses moving behind it. That's very hard. As I say, we have new projects even more ambitious than this to try to see if we could someday entangle these kinds of spheres floating in the center of some chamber through gravity alone. So these are really hard experiments. I'm not going to be talking about anything as hard as that in this talk, but we're still very interested in these kinds of applications. We've also tested the neutrality of matter. So once you have this ball that has exactly the same number of electrons and protons, is it really perfectly neutral? So we've done the world's best search for milli-charged, maybe dark matter particles with a charge, a fraction of an elementary charge, maybe 10 microcharges that could form some sort of funny Bohr atom with a silicon nucleus in our sphere. And in fact, we've ruled out that at least under standard calculations of how much dark matter should have built up on Earth and thermalized and formed these kinds of bound states, these kinds of experiments disfavor that less than a part per million of the dark matter around Earth is has a charge above 10 elementary charges, 10 micro elementary charges. You can also do things like test charge quantization, test the sum of the proton, neutron, and electron charge. We know that's 0 to 21 digits, but it's a measurement we've been doing for 100 years that we haven't improved in 50, and we'd like to do better. In fact, we're super excited about some work in Jack's group to maybe use superfluid helium to try to do this stuff. But what I'll focus on in this talk is the bottom, which is maybe the simplest thing you can have. You just have a sphere floating there, maybe harkening back to what I talked about at the beginning. Maybe a dark matter particle flies by and gives it a little kick. Or in fact, you implant a radioactive nucleus into the sphere and a fundamental particle leaves and you feel the force from that. So both of these are just like a little floating sphere getting a little kick that we can try to resolve. So let me start with the dark matter application. So if there's one thing you remember about this talk and how we can even claim we're doing dark matter with these kinds of tiny little sensors, it's maybe this. So if you've seen a talk on dark matter detectors before, especially WIMP detectors, particle dark matter detectors, they kind of look like some giant tank of tons of xenon. And maybe, there's a dark matter particle coming by and it scatters from a nucleus inside that xenon. And in fact, we know from the kind of properties we expect for particle dark matter around the Earth and in this mass range that this dark matter is not going to transfer enough momentum to resolve the individual constituents of that nucleus. So it's going to coherently scatter from that all the neutrons and protons in that nucleus. And so in now switching to particle physics units, maybe the inverse momentum transfer is about a picometer. This nucleus is a few Fermi. And so this is just fully coherent over a whole nucleus. It turns out then that when you're in this case, the way you actually see a dark matter signal is you have some incredibly tiny cross section for dark matter scattering from a single neutron, which might be relevant in the early universe. You get a nice enhancement of that because there's maybe in xenon 100 neutrons and protons here, and you add up all the amplitudes from scattering from those and then square it. So you get like a 10 to the 4 enhancement from that. But then you really win by having tons of this stuff and you have Avogadro's number and then some of specific nuclear targets in there. So these are quite large numbers and can go from a tiny cross section to an observable rate of maybe like a scatter per year or something. We're not looking for those kinds of models because we don't have tons of stuff. Instead, we're looking for things much like what I talked about at the beginning of the talk. We have a dark matter particle which flies by and then coherently kind of gently pushes on the entire nanoscale or microscale ball of stuff rather than hitting one nucleus or one electron hard. So now we're taking this coherence and supersizing it rather than being coherent over a single nucleus. We're looking for models that can be coherent over an entire macroscopic chunk of matter. And in these cases, there's kind of two generic mechanisms for that. One is that dark matter interacts via, a long range force, something like gravity. This is exactly how that thing I talked about at the beginning would work. Gravity, doesn't just hit one nucleus hard as it flies by. It coherently pushes on the whole ball. So we'd love to see something like that. But even if we can't see gravity right now, we can already look for forces between dark matter and normal matter that are long range, but are still weak, but much stronger than gravity. It's one way to do it. The other way to do it is just to, again, just take the exact analog of this idea, but move to much lower momentum transfers. So the inverse momentum is now big compared to maybe a 10 nanometer particle. And then the momentum transfer, again, now not only can it resolve a single nucleus, it can't resolve the nuclei within the ball. And we also get a coherent enhancement where the amplitudes add up before squaring there. And then we start with the same tiny neutron dark matter cross section, but now our coherent enhancement, instead of being 100 squared, maybe for our nanoparticles is 10 to the 9 squared, maybe the microparticles 10 to the 14 squared. And these are numbers that get really big. So maybe they rival Avogadro's number. We can still reach astrophysically relevant cross sections, but just with femtograms or nanograms of mass. And of course, we want big arrays of these, as I'll say. Okay, so just to show you can do this, actually right after COVID, when we got back in our lab, we did a proof of principle for this idea of looking for a long range coupling between dark matter and normal matter. So we just took 5 days of data with a little sphere floating there in the center of the vacuum chamber and looked for kicks that give it a little kick. This is a plot of the kicks we observed per day as a function of their amplitude. In SI units, this would be like, I don't know, 10 to the minus 18 Newton seconds, but it's more natural in particle physics units, GeV per C, where the C's are set to 1. So this is a force, an impulse of GeV, a momentum transfer of GeV momentum. The data we see here actually initially is the gray line here. That's all the events we see. And there's our Gaussian noise. And then there's this huge tail of kicks, much bigger than our noise. Turns out, though, this was during COVID, and there was one postdoc who was especially noisy in the lab. When we cut out the time periods he was there, we go from that down to here. So we're definitely sensitive to acoustic noise. Who knows what he's playing music or something. We also have an accelerometer on the table because we're aware of this acoustic sensitivity. And when we cut out those, as well as ensure that those kind of you drop a hammer sort of events often come in bursts, and we cut out things correlated in time, we end up with the black points here. And in fact, we mostly see our Gaussian noise over many orders of magnitude, and then there's 4 candidate events consistent with kicks above our noise spectrum in this case. Of course, this was the first search of this type, and we had really large backgrounds from acoustic noise that we had to cut out. So likely these are just not fully rejected acoustically transmitted impulses to the sphere. But to be conservative, we assume they could either be such background events or dark matter. In fact, the expected spectrum from dark matter is here kind of in the dark blue line. And so we can place limits on the strength of a coupling, any generic coupling between dark matter and normal matter through a long-range force. This is kind of a featureless plot. It's the limit on that coupling where this alpha is just the effective fine structure constant in a 1 over r, maybe Yukawa type potential versus the mass of the dark matter particle. We do in this paper assume a specific microscopic model, and essentially we've chosen models where LZ, those big tanks of xenon, other even extremely low threshold detectors are all way off the top of the plot. And this is maybe the first search of this type that really looks for these generic long-range couplings that would be scattering in xenon detectors all the time, but never produce enough energy to hit a single nucleus hard enough to see it. So this is really, just out of the box, the first proof of principle. Maybe so I can get to the second part of the talk, I'll go quickly over this for the experts, but we've also written a proposal to do this thing where we coherently scatter over the entire sphere, even if the force is not long range. If the force is short range, like the weak force that the W in WIMP stands for, it's not this case where you just intrinsically scatter with the whole sphere. But if the momentum transfer is so small that you can't resolve the individual nuclei in the sphere, you still get this coherent enhancement in rate. And maybe for the experts, this is the spin-independent single neutron scattering cross-section for low-mass dark matter sort of models. These are experiments like CDMS, some so-called low-threshold dark matter experiments here in orange. The mass here is maybe 100 MeV on this left plot. If we zoom out of that plot so that this left plot is this blocks, and we go all the way down to masses of order 10 keV, this is about as low as you can get before dark matter is moving too fast to be cold dark matter. We actually think we could get to extremely low dark matter masses. These things would produce incredibly tiny energies in detectors, so they fall way below the energy thresholds of most dark matter detection technologies. But because we're looking for these momentum transfers directly, actually we can get down maybe with this kinds of coherence to picobarn cross sections down at the thermal 10 keV dark matter limit. So again, sorry, this is mostly for the experts and I'm going quickly, but I'm happy to answer questions on that. But let me just say again, this is really, I think, very much the early stages of this work. We've done maybe one proof of principle. We have some proposals out, but it really looks like mechanical particle detectors for dark matter can just search for new classes of dark matter that existing detectors can't. And the next steps, of course, are to make the noise better, push down to this, for our big particles, push to this measurement regime where our measurement is the dominant source of noise, and then be smart, like Heisenberg told us we could be, and only be sensitive to the momentum and not the position of the particles, and go beyond that. So that pushes to the left to lower momentum transfers for a given size particle. But then, of course, once you have one, as I said, you want a lot. And there's been a huge explosion of work in making these arrays of optical tweezers. In fact, in the atom community, especially driven by quantum information applications, where huge arrays of Rydberg atoms for quantum computing. This is a beautiful plot, recent plot from Manuel Andres's group at Caltech showing 6,000 atomic qubits in these kinds of laser tweezer traps. There's like literally $1 billion flowing into that field right now. So we don't have 6,000 yet, but we're hoping that this really pushes ahead the scale that you can imagine these systems at. And in fact, we, as I showed, Ben has 25, but we want to try to keep pace and grow bigger and bigger arrays of these as we go. So this is just showing that same kind of parameter space. Again, a generic coupling between dark matter and neutrons in this case, long-range coupling on the vertical axis versus the dark matter mass. That proof of principle search is here in blue. And what we think we can already do, maybe in the relatively near future, just scaling these arrays to how much laser power we have now at our current noise and maybe a little better noise, We can push down already. This is like, yeah, literally 4 or 5 orders of magnitude lower. In the first proof of principle search, we were sensitive only to kind of composite dark matter particles made up of many constituents. But if we can get down below 10 to the minus 12 in this coupling, we can even see single particles. And then, I advertised at the beginning of this talk, maybe someday we can dream, ask the thought experiment question, can we do only gravitational coupling of sufficiently heavy dark matter? For full disclosure, in these units, that's at 10 to the minus 19. So it's another many orders of magnitude to go, but who knows if we have millions of tweezers someday for quantum computers, we could maybe imagine millions of spheres, and you have to go a lot farther. So don't imagine that's enough, but we, I don't know, we'll see. And even if we don't get there, maybe there's lots of just completely unexplored parameter space in this generic class of models where dark matter is just like mostly pushing on lots of stuff rather than hitting one nucleus that nobody's been able to look for before. And one last thing before I go to the next part is if we did see a signal in these mechanical detectors, it actually would be definitive. We'd be really sure it was coming from dark matter. And that's because we're measuring the vector momentum of these scatters. And because the Earth is going around the sun's going through the Milky Way with some funny proper velocity, we basically see this wind of dark matter coming at us from the opposite the direction the sun is dragging us along in the Milky Way. And as the Earth turns, we actually would see throughout the day these scatters coming from a different direction. Turns out just randomly in the spiral arm we're going in the direction of the constellation Cygnus. So if we saw some signal in the lab always pointing towards Cygnus in the sky, we don't know of anything that could know about that except something coming astrophysically. And so that would be kind of smoking gun evidence it was a dark matter signal if we see something. Yeah, exactly. Let's hope not. So in the last couple minutes, let me tell you a little bit about some other weakly interacting particles we want to use these sensors for. Neutrinos. In fact, you may know about these 3 neutrinos, but especially maybe there's some sneaky 4th neutrino hiding back here we'd like to look for. So I told you we can see, forces that correspond to a single dark matter particle scattering from the sphere. Of course, that means those are really fundamental particle level momentum transfers. So we can also just see forces from a single nucleus decaying if we put the right nuclei into the sphere. And maybe there's 2 kinds of obvious things to do. For radioactive nuclei, we can put an alpha emitting isotope in where the nucleus decays and emits an alpha particle, 2 protons, 2 neutrons. That flies out. That's the only thing that comes out basically in the whole sphere. The nucleus recoils, but it stops inside the particle, rattles around in some very messy way. But momentum conservation guarantees no matter how it stops, that whole sphere has to recoil with equal and opposite momentum to the particle that left, whether we detect that particle or not. So that's interesting for alpha particles, but maybe even more interesting for weak decays, beta decays, and electron capture decays, where the simplest case is electron capture. This is an isotope that would like to lose a proton maybe by emitting a positron. Doesn't have enough energy to do that, so instead it captures an electron from its atomic shell. And then a high energy and a high momentum neutrino comes out, and basically nothing else. The sphere recoils with equal and opposite momentum to that neutrino. There's some lower energy Auger electrons and X-rays that come out as the atomic electrons rearrange. But we don't actually have to worry about these because most of the momentum is just going out with that neutrino. And so again, we would see the sphere recoil, and we'd be able to detect the momentum of that neutrino on an event-by-event basis. This is exciting because that neutrino would go through a light year of lead before interacting. So we have no hope to see that neutrino by stopping it, like in the same way we could see the alpha particle. And this would be a way to study individual neutrinos coming out of nuclear decays. And then maybe the only tweak on the previous thing with the dark matter searches, again, we want a big array of these things, but we're now going to surround them with conventional particle detectors to see this alpha or maybe the Auger electrons and X-rays that come out. We can also do this with beta decays, as I'll say. So maybe just to give you a concrete motivation for what sorts of things we could test by doing this, although generically we're just looking for any kind of invisible stuff coming out of nuclear decays that we haven't seen before. But one obvious thing that a lot of people are looking for are so-called sterile neutrinos. And again, sorry for the more junior folks, but the 1-slide summary here is that we always used to have kind of massless neutrinos in the standard model, but one of the very exciting things that we've learned from Kirsten Heger's work and others in the past decades is that neutrinos oscillate as they propagate. It means the electron type neutrino, maybe that comes out of a beta decay, it's actually a superposition of the real neutrinos that have well-defined masses, which unimaginatively we call nu1, nu2, and nu3 with masses m1, m2, and m3. So we have some superposition. That's actually the interacting state. As that state propagates, because these are all slightly different masses, if they're massive, then the probability to detect some different interacting neutrino after some propagation in time or in distance changes. So we say neutrinos oscillate. Also, we've never seen a kind of right-handed neutrino or a left-handed antineutrino coming out. So we've only seen left-handed states in these kind of interacting states. And that's also kind of fine before these are massive. But now once you have massive particles where you don't have left-handed states, we're a little stuck about how we add masses for those in the standard model. It's not impossible, but in your standard kind of way you have masses in the standard model, those mass terms mix the right-handed and left-handed states. And so we think we probably need, unless we want to give up on some really fundamental symmetry principle in the standard model, we probably need right-handed neutrinos out there. One kind of heuristic way to think about it is if I have a massive left-handed neutrino, it's fine, helicity neutrino, because I can never boost to a frame where it's not left-handed. Once I have masses, there's some frame where I can boost to, and I would see that left-handed helicity neutrino flip. So why haven't we seen these right-handed neutrinos? Well, maybe they're sterile. That means they don't interact via the weak interaction like the other neutrinos. Things that only interact via the weak interaction are already incredibly hard to detect, but if they don't even interact that way, maybe only via gravity, we essentially have no chance of detecting them, except maybe, and it's somewhat natural to assume that the light electron interacting neutrinos that we have might mix in some fourth kind of new neutrino state that we haven't seen yet. It's mostly sterile. It turns out that in the range that we're sensitive to, actually, these are perfectly good dark matter candidates. So there's nothing that says that just adding a right-handed neutrino in the keV to MeV mass range couldn't make up some or all of the dark matter. So some people call these minimal dark matter candidates. This is a pretty complicated plot, but showing the mixing of this kind of possible heavy state with the light neutrino or with the electron type neutrino as a function of the mass of that new state. The best experimental limits in the lab are all these colored regions up here. And the relevant region for dark matter is maybe down here, maybe 7 orders of magnitude beyond what our existing experiments can do. And so we'd love to have experiments that could actually search this unexplored range and maybe really look for these kinds of heavy sterile neutrinos over a big range where they could be astrophysically relevant dark matter candidates. And the idea here is just to look for the wrong momentum of the neutrino coming out of one of these weak nuclear decays that emits a neutrino. And so I'll say a little bit more about that, but basically you can think of this axis talking about this mixing as being the branching ratio. What fraction of decays of a given isotope would emit one of these heavy neutrinos? And we can currently say no more than 1 in 1,000 of them do in this mass range, but we'd like to get down to like 1 in a part to 10 to the 10 or something. Okay, so what would this look like with the spheres? So if one of these heavy, maybe in this keV to MeV mass range sterile neutrinos mixes with the light neutrino, as I said, what we expect is that a small fraction of decays, if you emit that superposition, something measures something, and eventually you collapse that, you get one mass state coming out. And we'd see that as a kind of a branching ratio to a heavy decay. So if we were to measure many of the kicks from many of these decays acting on the center of mass or a nanoparticle, maybe for our favorite isotope here, argon-37, and make a histogram of the counts we observe versus the reconstructed momentum of the neutrino that we see from the sphere recoil. Most of the time, the sphere is going to recoil with the momentum as though the neutrinos just have the light neutrino masses. But every now and then, if we zoomed in here on the horizontal axis, we might see, for instance, if there was a heavy 750 keV neutrino mixed in with the electron type neutrino at the current lab limits, then just one of our spheres for a month, if we can put the right isotopes into it, would show like a very clear peak. And I'm drawing this without backgrounds, and as I'll say, we actually think this can be extremely low background. So already just at a month of data, maybe we could reach the best previous laboratory searches, and then of course, maybe imagine going many orders of magnitude beyond. So that's kind of what's shown here on the right. This is again, this kind of mixing or branching ratio of these decays versus the mass of the neutrino. The best laboratory limits are again in gray. And then what, we still have to show you can do this. This is only projections, but what you could imagine writing down if you had 1,000 spheres for a year actually really does reach these many orders of magnitude beyond, provided that we could keep these things at extremely low backgrounds as we go. So we think this is pretty exciting. And the other thing I should highlight is we think we can shove basically whatever we want into this glass matrix of the particle. So we're not trying to laser cool a specific atom. We can put whatever nucleus we like and hold on to it with a laser talking to the glass rather than the nucleus. So just to show this is possible, this is actually really nice work by our senior graduate student, Xiaoshang. And we've shown you can do this with alpha decays as a proof of principle on the way to neutrinos. So alphas, of course, have a lot, they're much heavier, they're GeV mass particles, they have a lot more momentum than a neutrino coming out, about 100 times more momentum. But we can already see them even with our relatively large spheres. Turns out, as I said, we have the sensitivity to do this. The main challenge is that we don't want to inhale radioactive spheres. So we have to find out a way to get the right radioisotopes into the sphere without contaminating the lab with a ton of radioactive dust particles. Xiaoshang found a really nice way to do this, which is complicated only because we want to make sure we're pretty safe about it. We start with radon-220, it turns out. That decays to polonium ions, which we can drift onto the spheres with an electric field. Those polonium ions half the time decay with an alpha coming out, implanting a lead nucleus inside. And then that lead has a 10-hour half-life, so we can pump down the chamber, and then there's actually 2 decays, bismuth-212 and polonium-212, that emit alphas in the next tens of hours that we can actually observe the alphas from. So we can do this all in the chamber, and then everything decays away in a few days, and we're not worrying about dust all over the lab. And we can do this. So actually, when Xiaoshang was able to stick these in the particles, we can see individual nuclear decays occurring in this dust-sized particle. Actually, the easiest way to see is just by monitoring the net charge. As I told you, we know exactly the difference in electrons and protons we have on the particles because we're applying a little field, measuring the net charge of the particle with its motion. This is showing that charge over many tens of hours. And actually, you're seeing every time this steps up here, which means losing electrons, each one of those is a single alpha or beta decay occurring in the sphere, and we just can't miss it. Like we have, essentially perfect ability to see a single nucleus inside that sphere decaying because charged particles, alphas and betas, come out and change the net charge of the particle. Of course, we don't want them to get too charged, so in pink here, we're applying, adding electrons back to the sphere to keep them neutral. Turns out, you might have thought 2 protons come out, they should lose 2 positive elementary charges. In fact, we always see, as I'll say on the next slide, we always see these things losing electrons, which is kind of interesting. In fact, this is a spectrum. If you take a histogram of all those charge changes we saw, we actually see some events that lose as many as 100 electrons, which we really didn't expect as these alphas and betas are blowing out of the surface. They're kicking out, a tiny amount of their energy is going into kicking out very low electrons. And in fact, most of what we think is the alphas, although we're confirming right now, maybe kick out 8 electrons, and the betas tend to kick out 2 or 3 electrons, we think. And to our knowledge, this is essentially a background-free tag that a decay occurred in the particle, because when we don't put these radioisotopes in the particle, as I said, we have 100 rontoamps of current flowing on and off. And even those rontoamps are single electrons coming on and off, or single ions. And we essentially never see events kicking out multiple electrons at the same time, except these nuclear decays. So in coincidence with the recoil, seeing a hit on our detectors, we think maybe we can get to incredibly low branching ratios. Even maybe more exciting is that at the same time we see this charge change. This is now a zoom in on one of those charge changes where you see we start with 7 extra electrons and we go to 13 extra protons here. If you look at the same time, monitoring the X, Y, and Z motion of our sphere, this is now calibrated so we can convert it into kicks, momentum impulses, and MEV. And we see a really clear high signal to noise peak here correlated with that charge change. If you zoom in here to that decay time, in orange here, we're actually plotting the position of the sphere. And you just see this damped harmonic oscillator response. It's ringing by a few nanometers. The decay happens and it moves by like 20 nanometers, which is exactly the momentum we calibrate to expect from a single alpha particle coming out and pushing on the nucleus stopping and pushing on the sphere. So to our knowledge, this is the first ever kind of mechanical detection of the force from a single subatomic particle pushing on a much more massive. This particle is trillions of times heavier than the alpha particle that came out. And because we can monitor its center of mass so precisely, we can see that. So in the last minute, let me just tell you about the next steps. Actually, it's already interesting that maybe measuring individual nuclear decays in dust particles, you might not be surprised to hear, as applications in nuclear safeguards and forensics. So we're starting to think about that because we can really see maybe 1 decay per day in these really tiny particles, and even long-lived isotopes could be detectable. But in our group, of course, we really want to push down to seeing single neutrinos. It's kind of 2 pieces of that. The first, Tom, our postdoc, and Jackie, our new student, is working on being able to take a bunch of radioactive nanoparticles in a jar of liquid and inject those into a Paul trap so that we don't spray radioactive nanoparticles all over the room again. And then we can transfer those into the optical trap while just loading, the minimal, absolute minimal amounts of radioactivity. And we've had some nice results showing we can make these little tiny droplets, and hopefully are incorporating this soon. Lucas and Zhashang have also been installing particle detectors. And I'll just say, we have now position-sensitive energy-resolving particle detectors here with that lead-212 chain I was talking about that can tell us the secondary particles hitting the detector at the same time we see the recoil. And maybe even more exciting, this is hot off the press, but Yuhan, our student's been leading this. We have reached the required sensitivity to see individual neutrinos with our smaller 100 nanometer diameter spheres. This is actually showing the motion of one of those. It's sitting there ringing. We put one electron on it and give it a kick with an electric field. This isn't a neutrino, but it's the same force that a neutrino plus a gamma would give it for this specific decay chain we're using. And just by eye, you don't need any fancy reconstruction here. You can see it's ringing, it gets a hit, it's ringing more. And so we have quite high, this is a histogram calibrating it many times. We have signal to noise above 10 to actually see neutrinos and gammas coming out of this thallium isotope in that same decay chain. And in fact, for these smaller particles, this works now within about a factor of 3 of the standard quantum limit. So we're really reaching this regime where the measurement itself is the dominant source of noise, and the thermal noise at this point is subdominant. So this is exciting also because we want to reach that and go beyond, do fancy things like squeezing, other things to keep improving. So let me stop there. I'll just leave this up. I think we're building these really sensitive force sensors that actually can see forces from single fundamental particles. We've already, I think, done some exciting things, but really, in my mind, the future potential of these, most of the potentials in the future, and we'll see what we can do at this precision frontier of nuclear and particle physics with mechanical sensors in the coming years. Thanks very much.
So much for the nice talk. We have some time for questions. Let's make sure we use a microphone.
And David, I have a comment and a question. Comment is another limit on sterile neutrinos can be put for the non-observation of neutrinoless double beta decay. And we did a calculation for that and show that the sensitivity is mostly for sterile neutrinos of mass about 100 MeV, which is the Fermi momentum in the nucleus. And perhaps in that figure, one will need to put that as well.
Yeah, so this same paper has exactly the limits you're talking about. This was trying to be just the laboratory limits that are assumption-free, but you're right, if you assume it's Majorana neutrinos and it enhances the rate the way you're saying, that's also strong constraints. Yeah.
Okay, so that's the comment. Then the question is, if you go down to electron capture in argon, could you show that picture? So what you see there is probably the K line. What about what you see there not being the L lines, L1 or L2?
Yeah. So actually the beautiful thing about measuring momentum rather than energy is all those different electron shell captures carry significant energy compared to the nuclear recoil, but their momentum compared to the recoil is barely different. So when you measure momentum, all those things are in here, but they're below the resolution of our momentum measurement. And so we're not going to be sensitive to those.
You are not going to be sensitive.
Yeah, something like BEAST actually, an energy resolving detector trying to do this kind of physics, their major concern is being limited by those kinds of effects. But if you measure momentum instead of energy, all those Augers and things with slightly different energies have much lower momentum than they do this MEV neutrino coming out.
Okay, and then related to this is, why not you do holmium-163?
Yeah, so it's a good question, but mostly because of the specific activity. The decay half-life of holmium is so long that, shorter tens of days half-lives are ideal for us. So things like argon are kind of ideal.
Okay.
Any other questions? Yeah, clear.
Hey, this might be a silly question, but way back on slide 12, you were talking about how it takes a couple days to get the microsphere spinning at its terminal velocity. And I was wondering what exactly determines the amount of time? Is it simply just because of the inertia of the sphere, or is there some other, even in high vacuum, is there some other kind of resistance happening?
Yeah, no, it's a great question. So what limits how fast we can spin them is how much torque we can apply. These are like amorphous silica spheres, which you wouldn't expect to care about the polarization of the light we're using. We're actually a little surprised to see this. They just have some trace amount of absorption or kind of ellipticity that lets them get a little bit of the kind of angular momentum from the beam and transfer it to them. If we had crystalline materials like quartz, we could spin these up like, 10 to the 6 radians per second or something.
Okay, gotcha. Thank you.
Thanks. Any other questions? Yeah, Leonid. Do you mind?
Thanks for very nice talk. I think that we actually have a question together with Keith. So you had this towards the end, you had this alpha particle that basically kicks out lots of electrons just because of impact ionization.
Yep.
So twofold question. So one is that perhaps the energy of alpha particles. So maybe one can estimate, how much electrons you kick out. But another question is actually is, so from time to time there are some muons, I guess,
Yep.
That are coming from outer space.
Yep.
In principle, they're also high energy, like they can deposit like kilo or even mega electron volt. So why don't you see these kind of things?
Yeah, so great. Well, I'll answer the second question because I have it in my mind right now. We get 1.6 muons per year in this geometric cross-section. So if these things are so tiny, the direct hits even at the surface are only 1.6 per year. And you're right, if they hit this thing, we're gonna see a ton of charge blasted out of here. And so for dark matter searches, those just aren't backgrounds. We don't necessarily have to go underground because we'll always see that some charged particle hit it. We do worry about things like neutral gas collisions, like residual gas in the chamber. There's some like radon floating around in the chamber at extremely low partial pressure that could hit it and give it a kick. But most of the radiogenic and cosmogenic backgrounds you have in normal detectors don't show up here. And even if they did, you're right, we would see these same effects and throw them out.
Okay, so it's just throw them out.
Yeah. For the first question, which is, how much should we expect here? Our collaborators have run a J-on simulation and like your standard particle physics tool for simulating MEV particles going through matter, and they just don't get this right at all. They way underestimate the charge that comes out of the surface. Underestimate. And that's because there's super low energy electrons coming out, and J-on just doesn't get that right. To our knowledge, there's maybe a little bit of previous literature on this, especially for metals, but for dielectrics, nobody can really see like a 1 eV electron popping out along with an MEV, alpha particle shooting out of the surface. So presumably there's in fact, we've simulated there's all kinds of silicon and oxygen, secondary nuclear recoils. Those are hitting electrons too, and you just get this like shower of down to extremely low energies of stuff coming out. One place this might be interesting is these are in all surfaces. They're in the tables. They're in your ion traps for quantum computers. And if you have these puffs of 100 electrons, slowly moving electrons, going through your million qubit ion array, the superconducting detector folks have recently seen phonons bouncing around and causing athermal interactions in their arrays. Maybe someday the ion folks are going to start to see these kind of correlated signals of many electrons passing through. But to our knowledge, there's not other measurements of this.